A buzzing?
Yeah.
It's the Apple TV that's on. Yeah. it comes
No,
from-
wait.
It's from
No,
the
not
projector.
that. That like the yeah.
Oh, I don't hear
I
Okay.
think
I definitely hear you.
Yeah, no,
Anyway.
not that.
Okay, so if I were to spin the wheel and ask you which way it's spinning, what would you say?
Left.
To your right.
What's going on?
You're right or left.
Wait.
Circular.
Yeah.
So the point being, is it easy to describe how it spins? Yeah, not really. Okay. So left, right, you might say clockwise or counterclockwise, but to you it's one way, to me it's the other. So what scientists did was they came up with the right-hand rule. And in your notes you should have a spot to fill in the blank. Right-hand rule is going to tell us the direction of angular momentum. I guess they picked the right hand because most people are right-handed. Is anybody in here left-handed? You actually have an advantage. If you're right-handed, whenever we try this, you're going to have to put down your pen or pencil and then keep your right hand free because you need it to do the rule. So I'm going to spin the wheel. The way you find the direction of angular momentum is to take your fingers and you curl them around and make them point in the way that it's spinning. So in this case, it's going around like that, so I'm going to curl my fingers this way. Okay. Which way is your thumb point? Up. That's the direction of angular momentum. Okay. So in this case, it would be up toward the ceiling. So no matter where we're standing in the room and which perspective you have on the wheel, the angular momentum is up towards the ceiling to everybody. So it just kind of gives you a better reference point to describe that direction. So we're going to practice with a few examples. So your fingers of your right hand curl in the direction that the wheel spins. Your thumb is going to point in the direction of the angular momentum. So I'm going to stand this way. And your choices are going to be the windows over there or the screen behind me. So is the angular momentum, is your thumb going to go to the windows or the screen?
That way.
Windows. Okay, good. So my fingers curl this way, and your thumb points to the windows. What about now? Towards the door or towards the windows behind me? Right hand. That's for your right hand.
Oh.
Curling this way. I'm going to have to move a little bit. So
I couldn't do it this way.
curling, so it's going the other way. So curling like that, and it happens to be pointing towards me, which would be the windows behind me. Fortunately, on a test, because we're limited by like the 2 dimensions of the paper, I can only ask you 2 versions. So on your test, I'll say something spins clockwise. Okay. So if you were to draw that on your paper and you drew a clockwise circle, curl your fingers. Does it point into the page or does it come out of the page? Your thumb.
I know.
Wait, what?
Mine hold on.
So fingers,
Pretty
see
much.
the
Oh,
arrows?
down.
It's going to go into your page.
Wait, what?
Got it.
Oh,
Cause like
So
if
draw
it's
on your
going this
paper.
way- Yeah, just draw.
So now your fingers, for you guys, your fingers, see, so point that way, your thumb's going to end up going down. So when you have that perspective and your fingers are curling in the way that something's clockwise, we're going to say that the angular momentum is. So we're going to spin. Okay, tilt it one way.
Yeah. I see what you
Tilt it
guys are
back.
saying. Like the other way. I can like pull.
Yeah, so when you
It does
flip it,
pull you.
yeah.
Look.
So what you're feeling is that angular momentum, because you know how your thumb points, you're constantly changing that direction, so it's trying to follow that.
This is actually kind of really fun.
What?
The angular momentum is like the direction of like the thumb.
So that's the direction of the thumb. So when you change that direction, it's trying to make you change in a different way. You have to follow it. So anytime it switches direction, something else feels like it has to spin to make up the difference.
I wasn't expecting it.
Oh my god, this is so heavy.
So go the other way.
This is weird.
See, it pulls you.
How
How did he go over there? I don't understand.
he just didn't stop it, like.
Yeah, you just let.
Oh, like
you
we
can
put,
twist your
okay.
body to work.
Save it.
That's water writing.
We don't
Okay.
have to draw that, do we?
No.
Okay.
On this, all I want you to get out of it is that if you change the direction the wheel spins, something else has to spin to make up the difference. Okay. If you wanted to take a picture or draw that, you're welcome to. I will explain it, but I'm not going to ask you to like draw that on a test or anything. Okay. So when we start and your thumb pointed up, okay, that was the direction of the angular momentum of the wheel. So this one was the wheel, and that was your thumb pointing up. Before you flipped it, did the person spin at all? No. So do they have any angular momentum? No. So the wheel plus 0 is just the wheel. So the wheel only had angular momentum up. The person didn't have any, so the total would be angular momentum up. Does that make sense? Okay, because there's nothing else that spins. Then what we're going to do is flip this wheel upside down. So now we're going to have its angular momentum pointing down. And I don't know if you noticed, but the person spins like this. So if you had to do the hand thing, which way is your thumb? Thank you for getting that quickly. Okay, so you're spinning.
Oh.
No, I'm so glad you didn't. Oh, I don't know. Just keep spinning. Okay. So, yeah. So spinning this way, we'll go slow. Okay. So I spin like this. So that's going to be your thumb up. I have a bigger mass, so the person gets a bigger arrow. So the person's arrow going up, subtract off the wheel's arrow going down, you should get the same total that you had before. Okay.
Same one on the before.
The same one on the before side before you flip the wheel. Okay. So the person has to spin to make up the difference so that you get the same before and after picture. That's all I care about you knowing. You don't have to draw it on your test. Okay. We observe angular momentum in a different way. So volunteers?
I'll go.
Okay. You get the other stool.
Is this one connected?
It's the same thing. So no. Okay, hold your arms out to the side like that. Lift your feet off like that. I'm going to spin you. And pull your arms in. Put them back out. Put them back out. Pull them in.
It's terrible.
It's tough.
Thanks so much.
Can we make you go the other way?
Promise.
Get motion. Okay. So, moment of inertia when your arms are out, big or small? Big. When you pull them in? Small.
I want somebody else to do that.
Got him.
What did you notice in the spinning speed when she pulled arms in?
It went faster.
Yeah, it went faster. So you want to try?
Got
Do
him.
ballerinas get dizzy like that when they spin?
No, they got
They
ice
don't-
skaters.
they
'cause I have
slide.
skaters on.
So
These are
fun.
heavy too, Claire.
They so like they look at one thing and they're like,
So they look at one thing, so when they're spinning, they do this,
It's like
and then they spin their heads really fast, and then
Oh,
finish spinning.
good.
Hair twirl. Okay, out. Ready? Arms in. Arms out. You feel the difference going fast and slow. Okay.
Can you keep going?
You're welcome to write everything. The red is what's important. Yeah, the top of the chair is not attached. Okay, so the angular momentum, which is the L, it's going to stay the same. Okay, so that side of the equation has to stay the same number. So when we talked about bringing your arms in, you were correct. That decreases your moment of inertia. So if the I in the formula is getting smaller, what's the omega have to do to balance?
Wait, what?
So the L stays the same. If the moment of inertia when she pulls her arms in, if that's making the I smaller, what's the omega have to do to balance?
Bigger.
Yep. So the omega side, your angular velocity, if that's increasing, that means you're spinning faster. So the moment of inertia and the angular velocity, they will be opposites to each other. Because the other side of the equation, the L, has to stay the same. So the moment of inertia is how spread out you are. Whatever it does, bigger or smaller, the angular velocity does the opposite, so you're going to spin faster or slower. Anyone still writing or have questions? Okay. So I just rewrote it a couple of different ways. Okay. So when we talk about the L side of the equation staying the same, that means that the angular momentum is conserved. It's like our collisions. The before and the after have to be equal. So the L has to be equal if you change something. And then the next slide just has kind of the same. I'm just going to move the slides out of the way. Maybe. So the ice skater, it's the same thing. On these, there's a lot to write. If you prefer to take a picture, I don't mind if you do that. So we've got the ice skater and a diver who's going to do a lot of flips. Okay. The ice skater is like you sitting on the chair. So you pull your arms in, that decreases the moment of inertia. So in order for angular momentum to be conserved, your spinning velocity or your angular velocity increases. So you see that as spinning faster. And if you apply it to diving, as soon as the diver jumps off the board, he goes into that tuck position so that he can do more flips. And what that does, if you go into the tuck position, does that increase or decrease moment of inertia? Decreases. You're tucked together, you're more compact in the middle. That's a small moment of inertia. So when that happens, their spinning velocity or the angular velocity is increasing. That allows you to go faster on your flips so that you can get more turns in. So the more tucked you can go faster to spin and do all your flips. What does the diver do just before they enter the water? Okay, they spread out. So when you spread out, what's that do to your moment of inertia?
Slows it down.
Increases it, and then in return slows it down.
So is that
Okay.
so you don't hurt yourself?
Yes. It's kind of like the impulse where you want more time so that there's less force. It's the same idea. You're slowing down the rotation so that you can enter the water more easily. And then last thing, who's strong?
Dana.
Here, Dana. Hold it like this. And you're just going to do this and go down. Okay. So straight over your head, quick, easy. Okay. Now we're going to spin it. Now do it. Straight. Much better. Okay. What did you notice and how it feels? Thank you.
It's turning.
Okay. It's turning. So just like when you sat on the stool and you try to move it straight, okay, whenever you flipped the wheel and made it spin, you felt that movement spinning. It's doing the same thing. So in your notes, you've got that one section that says precession at the bottom. For precession, what's going to happen, write this down. When you torque a top or when you apply a torque, to anything, it's going to wobble. So whenever you torque a top or apply a torque to something, it's going to wobble. That wobbling that you feel, that's called precession. So even if I set this on the ground, it's going to spin for a little bit, but then it's going to start to wobble. Okay. Notice your angular momentum is constantly shifting directions, so that wobbling, that's what precession is. So that's all you have to know about it. You get the precession by applying a torque, and then it's going to wobble, so the wobbling is the precession. And then also notice there is a Roman numeral 5 in your notes. You guys have to read about equilibrium. Okay. We'll have a lab on it next week to help you practice, but you do want to read that before we get here.